Thank you for listening to this forum podcast. Please check out our website for a rich archive of podcasts and writing from contemporary philosophers and other researchers on a wide variety of topics. The Forum is an educational charity dedicated to bringing academic philosophy to a broader audience. Please consider donating to us via our Just Giving page, which you can find on our website. Happy listening.
Thanks, Beth. Okay, let no one ignorant of geometry enter here. This, apparently, was the inscription engraved above the door of Plato's Academy. Not only was an understanding of geometry an important skill for his philosophers in training, but it was necessary to get into the building. To the casual observer, the persona of the philosopher and that of the mathematician might seem very different indeed, as different perhaps as the caricatures of the beatnik and the geek. On the one hand, Socrates, Foucault; on the other hand, Euclid or Andrew Wiles. And yet, the two disciplines have been drawn together again and again in their histories. Philosophy might be said to have something of a soft spot for mathematics. Mathematical truth, proof, and mathematical knowledge seem to represent irresistible special cases that the philosopher returns to again and again. Additionally, many phases in the history of philosophy can be seen as attempts to make philosophy about as similar as possible to mathematics, as disciplined, as agreed, as technical. Mathematics, too, has always had a special relationship with philosophy, especially with logic, that major root of the philosophical tree. Questions concerning how closely related mathematics and logic are, the consequences of developments in the one for the other, and questions of rigour and evidence have often been sources of fruitful interaction. Tonight I'm hoping for another such fruitful interaction, and I'm delighted to have four great minds of philosophy and mathematics with me to discuss some of the moments and topics that have brought philosophers and mathematicians into dialogue. Okay, so I'll just introduce our speakers. Mary Leng, at the far left here, is a senior lecturer in the Department of Philosophy at York. Her research interests are primarily in philosophy of mathematics and science, especially on the matter of whether the utility of certain mathematical assumptions in the empirical sciences should commit us to mathematical realism. She argues this case negatively in Mathematics and Reality in 2010. More recently, she's been looking at the relations between different kinds of fictionalism and parallels between debates over moral and mathematical realism. Tim Button is a philosopher working on metaphysics, logic, mathematics and language. He's a senior lecturer and a fellow of St. John's College at the University of Cambridge. He just returned from a period of research leave funded by a Philip Leverhulme Prize. During that leave, he wrote Philosophy and Model Theory with Sean Walsh, which is forthcoming with OUP. He's the author of The Limits of Reason, which explores the relationship between words and world, semantics and skepticism. Adam Ostaszewski is a professor of mathematics here at the LSE. His research interests include set theoretic topology, analysis, and probability. He's also interested in applications of mathematics to the social sciences, particularly in voluntary disclosure theory in accounting. His early work focused on mathematical logic, including model theory, and his name is associated with the club combinatorial principle. Nick Bingham began his mathematical life with a first degree in maths at Oxford, and then a PhD at Cambridge. He's a probabilist with interests also in analysis, statistics, history of mathematics, and mathematical finance. He taught at the University of London for 30 years, spending a time at Westfield and Royal Holloway, and then at Birkbeck, where he was reader and then professor, and at Brunel in Sheffield. He's now a senior research investigator at Imperial College London, officially retired, but still research active and teaching. Okay.
And visiting professor in the maths department here.
And a visiting professor in the maths department here.
Which is why I could get in.
Okay, so I'm going to give question one to the philosophers. Mary, Tim, it may come as a surprise to some that philosophy of mathematics is a well-defined discipline within philosophy. Could you tell us about some of the central topics on which a philosopher of mathematics might find themselves working?
Sure. Well, okay, as philosophers, some of the key things we're interested in fall under metaphysics, which is the theory of what there is, and epistemology, the kind of how we know about things. And maths presents an important test case for things we might want to say as philosophers about what the world's like and how we come to know it. So if we think of how we understand ourselves scientifically as physical creatures who come to know the world about us through our physical interactions with that world, it looks like the kinds of things we could know about are things that we come into causal contact with. Mathematics presents a problem for that picture because mathematics looks like it's a body of knowledge about objects that aren't physical things in the world. They're not spatiotemporal. Things like numbers, we don't bump into them in the street. And yet we still appear to know lots of things about numbers, and furthermore we seem to know lots of things about numbers with certainty. You know, it's 2 + 3 = 5 is about as certain as we get. So the trouble with numbers, we might want to say, is how can we come to get this kind of knowledge, apparently certain knowledge, about these things that we never come into physical interactions with, as beings whose knowledge of the world seems to be mediated through the senses. So maths throws up a bunch of interesting questions about knowledge, about the nature of mathematical objects. Our mathematical theorems appear to assert truths about mathematical objects, truths that we can know of with certainty. But that raises the question of what the nature of these objects is, and how is it that we could come to know things about objects of that sort. So if mathematical objects are, as we often think of them, as being abstract things, acausal, non-spatiotemporal, how is it that we can come to know them? How is it that when we find out things about these objects, it turns out to be the key to finding out things about the world of physical things? How is it that mathematical objects are useful?
You mentioned that they're acausal. I wonder what's the difference there between that and the kind of regular objects of science?
Well, even though we don't see things like electrons, nevertheless it seems that electrons enter into causal interactions. So we might see a trail in a cloud chamber and think, oh, well, that was caused by an electron, so that's evidence that there's an electron there. Mathematical objects don't, we also don't see them, but they don't seem to do anything like that either. It's not that, seeing the track in the cloud chamber gives us, it doesn't look like it could give us evidence for the number one being there. Number one isn't anywhere, right?
Thanks, that's really helpful.
Yeah, so I'd like to carry on with that kind of thought. So Mary mentioned some of the epistemological difficulties, and that's the questions about how we can know about these things. I think there's a prior question to that, which is how we can even have beliefs about them at all, how we can even have beliefs with determinate content if these aren't the kind of things that you can bump into. I mean, you might say I'm able to think about the table in front of me because I can see it and interact with it, and so I start to use the word table to talk about those kinds of things. But again, in the mathematical case, we don't seem to do anything like that. And there are particular mathematical reasons to wonder about this. So one of the things you might say is, well, what mathematicians do is they set up a formal theory, and then they derive consequences from that theory just using logical rules alone, and that's what mathematics comes down to. And a large part of mathematics does consist in something a bit like that. But then there's a question about just how precise we can be when we formulate our theories. So if the aim is we want to describe some certain area of mathematical reality, so we write down a bunch of axioms with the aim of characterizing a particular bit of mathematical space, and then we reason about it just by thinking about the axioms. Well, there's a difficulty, which is it turns out that we're not able to be very precise in formulating our axioms. There are mathematical results which say, no matter how precise you try to be in what you've written down, there are umpteen other things that you might have been talking about that you didn't want to. Now, obviously, that's a sort of informal characterization of a perfectly formal result. But it means that there's something very, very funny about the way in which we do mathematics. And yet, for all of that, mathematics is an absolute paradigm of how we have knowledge, as Mary said. It's also a paradigm of how we communicate. It's unreasonably effective in that regard. If you think about scientific theories, if someone comes along and offers a scientific hypothesis, then it can take a long time to settle whether or not it's right or wrong. In mathematical cases, if someone claims something, the mathematical community gets to work on the internet, and within a couple of days, it tends to be either settled that what happened was a real proof, or what happened was a failure of a proof, or, well, that's it. There's no in-between stage. So mathematics has this astonishing status of unreasonably easy to communicate, and yet utterly mysterious about how we can communicate it at all. And that's kind of why, as a philosopher, I think it's particularly fascinating.
Okay, yeah, it seems like there's some characteristics of mathematics that make it simultaneously ideal, but also really, really difficult. I'm going to ask you guys about numbers in a moment, but I wonder if you've anything to add to that kind of thought on the more philosophical topics.
There's only one number 5.
Rebuttal?
So
No, I agree.
there are
Sort of.
ambiguities, well, at least from the mathematical point of view, right? If you go to the infinite, there are indeed problems, and Tim was sort of talking about the Skolem paradox,
Yeah.
where this is discovered about the 1930s when mathematics began to gain more and more rigor and formalization, and Skolem said, look, we think we know all about the natural numbers, but actually when you write down all the axioms that people usually get taught in their first year of mathematics degrees, it turns out that they can be reinterpreted to include some infinite natural numbers, and all of this is perfectly consistent. So that's just an example of what Tim was saying, but that really is something that arises the moment you move into the infinite. And the moment you move into the infinite, you can go back and start thinking about the Greeks who were pointing out to all sorts of difficulties with the infinite. The paradox is Zenos' paradox. I don't need to mention any more. You sort of suggested, if I can still have a moment at the microphone, that we don't know what we're talking about. And there are some very famous statements like that about mathematicians. Nick's already noted to say that he's going to tell us that. He's the historian here. But the thing is that we have a visualization of all the things that we're talking about. Admittedly, it's inside our heads. But when we teach mathematics at secondary level, we always think of real numbers or numbers on a line, and that's our very first visualization. And what we do with that line, do we thicken it up to introduce imaginary numbers? Don't worry, but we're not going to say any more about that. Can you add more at the other end? Is there something at infinity? Or as Nick says, when he was a kid and he was drawing graphs and he was saying, this graph goes off there and then it comes back from the other side, disappears on the right, only to reappear on the left. I'll let him explain that later. So, you know, we do have ways of trying to plug the apparent gaps in visualization. And if I can just go back to the business that was mentioned about tracking particles in clouds, much as Einstein pointed to the existence of the atomic theory by pointing at Brownian motion and saying that's the proof that the thing you can't see actually is there. There is something vaguely similar in mathematics. The mathematics of the real line, nothing terribly complicated. When you take, you know, those numbers that have some particularly interesting property, it may turn out that in order to understand such sets of points on the line, you need to invoke the existence of certainly very large infinities, so big that the physicists wouldn't be interested in them at the moment, which have a definite implication for the here and now, from up above to here and now down there. So there is a sort of tracking phenomenon, if I can call it that. Of course, it's not the same as physics, but over to Nick, perhaps, or anyone else.
Well, I was going to, I mean, maybe it's a good time to move into this idea of the concept of the number and how it's changed over time. I guess this is one way for us to begin to think about a sort of conceptual or philosophical question that finds itself articulated nicely through the history of mathematics.
Well, could I invite you, ladies and gentlemen, to remember your first encounter with mathematics, which was undoubtedly learning to count. And I remember this very vividly. My late mother, who happened to be my primary school headmistress, was talking to me along these lines. I listened to the infants through the schoolhouse door, learning to count up to 10, and then up to 100, and then up to 1,000, and then I learned about millions, billions, quadrillions, and so on and so forth. And I thought this was wonderful stuff, and where did it all end? So I asked my mum. I said, "Mum, what's the biggest number?" And she smiled and said, "There isn't one." Now, why I don't know, because my parents were very open with me about things like where babies come from, that kind of stuff. But I got very cross and said to her, "Of course there's a biggest number. I want you to tell me what it is." And she smiled again and said, "No, there isn't one. There can't be, because if there were a biggest number, you could always add one onto it and get something even bigger." Now, some of you will be religious. I'm not. I have no religious belief whatever. But I can remember that moment. It was as if the heavens had opened and God himself had reached down and touched me.
That's why he believes in numbers.
That was my first mathematical experience. It was my first encounter with mathematical proof, which is the heart and soul and essence of mathematics. And it remains the most vivid mathematical experience of my working life. I'm 73 today. I've been a working mathematician all my life. Is there anybody here present who has any corresponding memory? Please show. Yeah. Wonderful.
My parents are over there.
Wonderful.
But
Right, ladies and gentlemen, many of you here will be parents. Do any of you remember anything like this with you as in the role of parents and your children visibly thinking their way through this sort of thing? If not, keep your eyes open. My kids know what to look for. I've got 3 grandchildren already. This leads one on quite naturally. 1, 2, 3, 4, ... Keep going, adding one on, ... Now, the things that we've just described are what are called natural numbers or positive integers, numbers to the man or woman in the street, and there are infinitely many of them because the list doesn't end. Some of you will share my love of French cinema. On the last frame of a French film, there's a 3-letter word beginning with F. Fin, end. Infinite means not having an end, and the list doesn't have an end, so it's infinite. Full stop, new paragraph. If you talk about the natural numbers, you're talking about an entity, one entity, with infinitely many things in it, and I hope this doesn't sound trite to anybody, because it certainly isn't. That is the great leap. The thing is that anything with a smidgen's worth of the infinite about it is beyond our direct human experience, even in principle, because life, ladies and gentlemen, is only finitely long, isn't it?
It's his birthday, that's why he's sharing.
Anything with a hint of the infinite takes us beyond what we can see, hear, feel, touch, smell, but not beyond what we can think about. That really is crucial. Okay, well, look, I feel in need of a pause for breath, so let me hand over to our lovely chair. Thank you.
Well, any responses from the philosophers there?
Well, I think it's true that once we move to the infinite nature of mathematics, that's what really opens up the important philosophical questions, because so long as you're thinking in finite terms, 2 + 3 = 5, yes, it's about numbers, but we can kind of think of that as being about things we can do. If I count 2 things and another 3 things, then I can count them in a different way and get 5 things. It looks like it's something that we could really understand as about something that we could do as finite beings in finite amounts of time. But when you move to the infinite, it's suddenly not like that. So although given enough space and time, I could, in principle, count to any large finite number, I can never count to an infinite number and complete that process. And that's what opens up some of the magic of mathematics from a philosophical perspective, that it seems to concern these things that we can't sort of straightforwardly reinterpret as about ordinary mundane experience of the world, as the infinite is not something we seem to encounter in reality, and yet it's a huge part of mathematics.
Yeah.
There's also a related thing that all of that gives rise to, which is it's very easy, as Mary said, when you talk about, say, 2 + 3 is 5, to think if that means if I have 2 apples and 3 pears, then I'm on my way to a fruit salad. But the crucial aspect about what just went on is we don't just use numbers for counting, we can also count numbers. So you can ask how many prime numbers are there between 0 and 10, and there are 4 of them. And then you can ask how many prime numbers are there in total, and a pretty similar line of reasoning will convince you that there are infinitely many of them. And it's that means it's not just the reasoning about infinity which gets complicated, it's also that kind of thought which means we have to treat numbers as objects in a certain kind of a way. And that raises lots of other philosophical issues again, like, well, what sort of objects are they? They're a bit funny in some sense. And so there's quite a lot bound up with that, a realization that you can count the numbers themselves, and that being partly what's responsible for them continually being generated, but also giving them a sort of objecty kind of a status.
Yeah, I think there's a good Russell quote, isn't there, about the infinite problem, where he says it's fine when we're at the sort of numbers that cover macro experiences, but once we start to get really big or really small, that's where the difficulty enters in. Either the sort of the role of the infinite in introducing difficulties, or the fact that counting numbers seems to be fundamentally different from counting
Well,
tables.
counting isn't a word that I would use here. Once you've got infinity in there, you're doing mathematics and you've crossed the great divide, because you can't prove anything. If you stick in a finitistic world, you can't do proper mathematics. Oh, by the way, why do we do mathematics? There are two fundamental reasons. I do it because it's fun, and indeed because it was my livelihood. But fundamentally, the reason mathematics is done is because it is so useful. Mathematics is the common core of all science. Science is the difference between the modern world and the Middle Ages. Without mathematics, there's no science, and without science, we're back in the Middle Ages burning witches. I don't know whether that's a new thought to any of you, but I really want to hammer that home. I'm based at the Imperial College of Science, Technology and Medicine, whereas here we are the guests of the London School of Economics and Political Science, which is science in a somewhat different sense. Economics, I'm teasing our host and my friend and colleague here.
Used to it.
Economics is called the dismal science. There is a sense in which anything to do with people, particularly interactions between large groups of people, is unmathematicizable, even in principle. Whereas electrons are much more amenable. They're spooky, but they're rational, whereas people are spooky and irrational too.
Can I throw in a thing about witch burning quickly? Well, I'm just slightly suspicious of the connection between the mathematics and the science side of things. We burnt plenty of witches in the 17th century, and Newton, who I'm going to talk about in a moment, did a lot of interesting things in maths and science, but his primary interest was basically in alchemy and in rainbows.
Well,
so it's not as neat a narrative as you might want it to be. I could plenty well believe in witches and still be a great mathematician. Unfortunately, I'm not a great mathematician, but also I don't believe in witches.
My friend is hinging something on using Newton as an example. Newton was such an extraordinary person that I would hesitate to base any argument on Newton. I'll actually tell you why. The three great names in mathematics are Archimedes, Newton, and Gauss. The two great names in physics are Newton and Einstein. The only name that appears in both lists is that of Newton, who was a horrible person, but he was a magnificent thinker. In some sense, I think he was the great man in the history of science, but I would say that the greatest single idea in the history of human thought has nothing to do with anything we've been talking about, and I would say it's Darwinian evolution. So much for you, Sarah, Newton.
Well, I wonder, is Newton the only example, though? I mean,
Right.
like Gödel might be possible to raise as well. But at this point, I thought maybe we might have some questions in the audience. Maybe Tim's parents want to tell us about his early mathematics.
Please don't.
Okay, so questions?
Well, I have a question that relates to what's just been said about what sort of objects the numbers are. But before I get to that, because I'm both a biologist and at Imperial College, by the way, and an economist, I want to take exception to the idea that science is all about numbers.
Oh, I didn't say it was.
Ooh.
Oh, I
No, he didn't say that.
He didn't say
we
that,
wouldn't
okay.
say that.
A lot of times one hears that. Anyway, because biology is basically about a lot of other things, and numbers play only part in that.
Yes.
Crocodiles.
The question I wanted to ask is about the probability, how to think about the laws of probability, because they're very, very successful,
Yes.
probability and statistics,
Yes.
and I've used them in my professional life for decades. So I don't have a problem with them being true as in the sense of being a good representation of the real world. But I find it interesting to think about the existence of numbers in terms of what sort of existence the probabilities have. Because on the one hand, they're obviously not an emanation from the ordinary human brain, because most people, it's well known, have a real problem understanding probabilities. You have to have a special kind of brain and training in order to think probabilistically. But also, I think there's good reasons for saying that they're not properties of the real world. De Finetti famously said, probabilities do not exist. And I think that's not everybody would agree, but I think that that's a well-founded statement, which means there must be some third kind of existence, which is neither kind of ontological, metaphysical existence out there, nor an emanation of our brain.
Well, we've got a probabilist and some people who certainly have views on the status of probabilities. But Nick, do you want to say a little bit more?
Well, I'd be very happy to. First of all, I'm delighted to find that we have biologists in the audience. Life sciences are wonderful. May I remind you of what I think it was Sir Robert May said, I think in his presidential address to the Royal Society, about the three frontiers of science as he saw it. The very big, general relativity and cosmology, etc. The very small, subatomic particles, and this was before the discovery of the Higgs boson, and the very complicated. And he said something I'll never forget, that the simplest life form is more complicated than a star. That's by the way. Coming back to probability, I take the view that the best you can do for thinking about probability to the man and woman in the street, and this is a general audience here, if you ask your granny, those of you who still have grandparents, what the law of averages says, your granny will smile and say, well, if you keep tossing a coin, dear, it'll come down heads about half the time. So an idea of symmetry between heads and tails, or between the six faces of a die, that will do you for finite probability, and to get from finite to infinite takes us right up against what we've just been talking about. And to me, that's it. You give me the real line and the mathematics that goes with it, and I can give you probability theory, which is what I do for a living. And it works as mathematics perfectly well, but it also is extremely valuable pragmatically to working scientists like yourself. So to me there's no problem, and as for De Finetti, I could talk about De Finetti for half an hour, but I would prefer not to, because there are people who feel passionately about this sort of thing, and I'd rather let them fight it out between themselves. I see no reason to get embroiled in that sort of thing. Does that answer your question, sir?
No, because there was supposed to be a third existence, I think.
But
Maybe we might ask Mary then, probabilities, do they exist?
Sure.
Any
Well,
way?
I'd like to draw a distinction between the mathematics of probability theory and then the thing it's representing in the world. So mathematics provides us with a really useful model, and then it's a question of, well, what's it a model of? And on some accounts it's degrees of belief, and on some accounts it's frequencies or objective propensities of things in the world. And perhaps it depends on what you're using the probabilities for, what the right answer to that is. Now that question is an important one, but it's not the one I'm interested in when I'm asking, well, what does the use of numbers in all this tell us about, in science, tell us about the reality of the numbers? And I guess what I'd like to suggest is, whatever we think that probabilities are modelling, we have this mathematical theory that works very well as a model of, say, propensities or whatever we want to take it to be a model of. Does the use of mathematics as a model in that way commit us to thinking that the objects, the numbers that we use in that model, really exist in any substantial sense? And the line I've taken on the use of mathematics in science has been to say, actually, it doesn't, because whether or not there really are numbers, or if we're just imagining that there are numbers that satisfy these axioms, as Tim said, there's a picture we can have that says, okay, well, look, in mathematics, we come up with axioms and we work out what would be true were there any things satisfying these axioms. The answer we give to that question doesn't really make any difference to the effectiveness of the mathematics as a model of whatever it is we're modelling. So I think there's two questions there. There's the question of what it is we're modelling when we use probabilities. Big question for philosophy of science. And then there's the philosophers of maths question of, well, what are the mathematical objects in our models? What is their ontological status? And there I want to say, well, whether they exist or not really doesn't make any difference to the success of mathematics as a model.
Can I chip in?
Sure.
I'm reminded of, well, I have two things I wanted to say. One of them, I'm quickly reminded of Roger Penrose, the physicist, writing a book this thick, which is very hard to read if you're not a mathematician, I think, called The Road to Reality. And this is a picture he keeps showing of three worlds, one of them being in our heads, the other being Plato's ideals that we pretend exist, right? And then there is this thing we're trying to learn about, which is the real world which we're trying to make contact with. And there is this whole business of how these things flow from one to the other. And that brings me to the other point, which is you may or may not believe that numbers exist, but even in Babylonian times it was important to know how many bushels of corn there were. And from Newton's time on, it became important to introduce these, and I think Tim wants to say a little bit about the incredible difficulties at the time, the use of infinitesimal calculus, which Newton saw as somehow a mathematics with yet another quantity that apparently isn't even visible, namely the infinitesimals, which were clearly in his mind and that of Leibniz. And what it enabled him to do was to simplify the business of calculating things like orbits of planets. And without this calculus, I was waiting for Nick to say it's one of his favorite themes. Calculus is what makes the difference between one set of people and another set of people, right? And so stop worrying about whether they are there. They have an absolutely tangible effect, unless you think the moon is only painted up there.
Lovely.
Okay, well, that seems like a decent segue into the next topic. I thought it might be helpful to look at a case study of a particularly troublesome number, which is an infinitesimal. So Tim, would you mind sort of leading out a bit on this? Could you tell us a bit about infinitesimals and why they've been such a source of consternation for philosophers and mathematicians?
Yeah, I'm more than happy to, but I'm going to go back a bit because we've been using the word infinitesimal for a few minutes and haven't quite said what it is. So I'm going to offer a slightly anachronistic historical reconstruction of how Leibniz and Newton came to discover them. So imagine you've got a car and it's driving in a straight line, and you've plotted its location at every given moment, and now you want to calculate its velocity. So that is, you want to calculate the change in the distance of the car with respect to where it started, divided by the change in the time. Well, one way in which you might do that very straightforwardly is if you just want to calculate the average velocity for the whole time that you're interested in. You just look how far did it go, and you divide it by how long it took to get there, and then you have the average velocity. But you might be interested in specific instances of when it had certain velocities. So you might say, let's consider the velocity of the car for the first part of its journey, or the first quarter of its journey, or something like that, and get increasingly refined average calculations of what the velocity looks like. But what if you wanted to know the velocity of the car at an absolutely precise moment? Well, you can keep estimating it in this way. Say, imagine what happens over the next second and see what the average velocity is then, or over the next half second, or the next third of a second, or just the next quarter of a second, and keep taking smaller and smaller intervals and getting better and better approximations to what the velocity at that given moment is. Problem is that's only an approximation. Approximations are all well and good if you're an engineer, but if you're a mathematician, you might well get quite frustrated by that. You want to know what the actual answer is, and not just within a margin of error that you no longer care about. So can we be more precise about this? Can we say what the velocity is at an instant? What happens in the limit, as it were? And for people tuning in on a podcast, I did a little scare quotes thing around in the limit. Okay, so what would happen in the limit, it seems, is you'd think, well, we were considering how far the car went in a second, then half a second, then a third of a second, a quarter of a second, a fifth of a second. So we want to know how far the car goes in 0 seconds, and that's presumably 0 meters. And then we divide the 0 meters by the time it took to go 0 meters, which was 0 seconds, which is 0 divided by 0, which is obviously bad. If you put that in your calculator, it will go, I don't really know whether people use calculators anymore because of smartphones, but when I was young, it would have said in the little binary thing.
Smartphones have calculators. My kids use them.
Okay, good. Well, in any case, it's bad. You're not allowed to divide by 0. That's one of the few things you're not allowed to do in mathematics. So what do you do? Well, it looks like what you want is an infinitesimal change in the time. You want to consider an infinitesimal little extra moment of the car travelling and work out just how far the car went in that infinitesimal bit of time, and then divide the distance by the time. But that just looks like you're cheating, because on the one hand, you want to say the infinitesimal has to be bigger than 0, because you can't divide by 0. But on the other hand, it has to be smaller than any real number, because otherwise you just have an approximation, and you don't want just an approximation because you're not an engineer, you're a mathematician, and you really care about absolute precision. And that's the problem. You want to have these entities which in some sense behave exactly like 0, except that you're allowed to divide by them without it being cheating. And that is a serious problem, because it does just look like cheating. Okay, so here are some fun facts. It sure looks like cheating. Here are some fun facts. So the first thing is basically, with a bit of anachronism aside, that's pretty much how Newton and Leibniz are thinking when they're talking about the calculus. And I've deliberately chosen a mechanical instance of this because the mechanics is obviously in the forefront of Newton's mind. The second thing is this criticism that it's basically cheating isn't anachronistic. Fundamentally, it's something that Bishop Berkeley was complaining about at the time, and people did take it seriously. There's lots of Newtonian acolytes trying to defend Newton, but they're all basically wrong. It is cheating what Newton's up to, and people do worry about it. But they don't take it that seriously, because although it seems like cheating, it's damned useful. So they carry on using these infinitesimals, these very naughty, badly behaved entities for a very long time, because it just works so fundamentally well. Now, skip forward a little bit. They end up getting banished. These cheating entities, people in the 19th century, Cauchy and Weierstrass, work out how to get rid of them. So the quick story there is, I asked what happens in the limit. They come up with a rigorous definition about what it means to talk about the limit, which doesn't involve postulating these cheating kind of entities, which are in many ways like 0, but not completely like 0. So they banish infinitesimals from mathematics for at least a century. And in some ways, that's a really good thing, and in some ways, it's a bad thing. The good thing is, it looked like mathematicians were cheating, and now we've worked out how to do what they wanted without cheating. And that's good. It's the advantage of honest toil over theft. The bad thing is infinitesimals are really useful to think about. It's quite a helpful way of reasoning about the calculus. But also, there's a lot of really beautiful mathematics that gets done using infinitesimals that if you get rid of them, you just have to throw away and say, well, unfortunately, this was all just cheating, so it's not really maths. It's just sort of fluff that was being generated at the time by a misunderstanding. And that seems like a very weird attitude to have, because the mathematics was beautiful, and these were really brilliant minds, and they were doing really fascinating things. And you might think that there must be some way of rehabilitating it. So here's the fun fact, the final fun fact. You can rehabilitate all of this stuff, but this has only become apparent in the last few decades. So I'm going to quickly, if I've got a moment, just sketch how you might go about rehabilitating it. So the idea works roughly like this. Suppose I want to explain to you about how an infinitesimal works. And remember, the aim is it has to be bigger than 0, but smaller than any bona fide real number that you're actually okay with. So I ask you to write down all of the things that you think hold for the real numbers, the line as you standardly imagine it. And you write them all down. And then I say, good. I now want to introduce a new name. It's going to be Teensy to remind you that this is going to be for an infinitesimal. And I now want you to consider infinitely many claims. Again, it's always coming back to the infinite. The first claim is Teensy is bigger than 0. Clearly we need that because we want it to be an infinitesimal. And then the next infinite series of claims of the form Teensy is less than 1, Teensy is less than a half, Teensy is less than a third, Teensy is less than a quarter, and so on for all of your numbers 1 divided by n. Teensy is less than each of them. Now I put it to you that Teensy, if it exists, has to be an infinitesimal because it obeys this thing that it was bigger than 0 but smaller than anything you were comfortable with. So that's good. And now you think, well, maybe I've just contradicted myself, though, because it does feel a bit like cheating. And I say, okay, well, what would it be for me to have contradicted myself? It would be that you can prove from what I've said, all of these infinitely many things about Teensy, that somehow some absurdity follows. But to show that an absurdity follows from the things I've said, you need to take a bunch of assumptions and derive a contradiction from them. Now, the fun thing about derivations is they have to be finitely long, because that's just of the nature of what a derivation is. So, given any finitely many things I've said, I will only have managed to say Teensy is less than 1, and less than a half, and less than a third, and less than a quarter, and so on. And I'll get up to Teensy is less than 1 divided by n. And I won't have contradicted myself, because maybe Teensy was just 1 divided by 2 times n, in which case it would have obeyed all of those things. So for any finite bunch of things I've said, it's completely consistent. So, because consistency sort of has to show up in finite bits, this is consistent overall. Okay, so that was a gloss of a genuinely technical result called the compactness theorem. But setting that aside, the basic idea is you can coherently get these infinitesimal entities back. Now, it's hard to imagine what they look like. It's hard to imagine how they behave. But having them back, we can use them in our reasoning about the calculus. And we can also rehabilitate lots of really elegant mathematics. So going back to the ways in which Euler used infinitesimals, we can actually recreate his proofs and show that he was doing perfectly wonderful mathematics, even though he couldn't have explained exactly why it's consistent to think about these things. So this is one of those moments which I think there was a genuine trouble with numbers, and a combination of some more mathematics and a bit of philosophy and some jiggery-pokery. And in the end, you get to rehabilitate something really, really wonderful. And that's one of the reasons why I'm both excited about the trouble with numbers and also excited to be able to contribute a bit to that. Because I should just now shamelessly plug something. It wasn't immediately obvious that you could rehabilitate these proofs until me and a guy called Sean Walsh showed that you could. So that's kind of nice. And yeah, go team Sean Walsh. It was mostly him, I should say. So then
Teensy comes out as not that much more problematic or equally problematic, let's say, as any other normal sort of real number? Or would you say there's any sort of special problems left there?
It's a very good question. I mean, certainly...
Can I save him from that question? Can I save him?
Yeah, please,
Sure.
please, yeah.
It's a standard trick in mathematics. Number 1, to think the unthinkable. And number 2, when you've thought the unthinkable, to give it a name. And then to just use the name to do all your like you've just named it Teensy or whatever, That was the situation when everybody said there is no square root of -1, right? The positive number squared is positive, a negative number is positive, 0 squared is 0, no good. When suddenly the mathematicians said, that's all right, let's give it a name and it's called I.
Give it a symbol, yeah.
Give it a symbol and call it I, and all you have to do is work with it, but remember that I squared is -1. And then you might think, yeah, are these guys nuts? And the answer is no, because eventually the wisdom of this becomes capable of being explained in various ways, such as a rotation through 90 degrees, when repeated, actually gives you -1, right? It turns you backwards. So why not think of the plane, and you've got your real line and orthogonal to it, perpendicular to it, another axis. Why not think of the plane as consisting of numbers? It was a remarkable idea, and a lot of mathematicians, Nick will say, when it really took flight, they all thought, well, sort of dodgy kind of mathematics, until it became the tool for electronics. You can't live without the square root of -1, and I think we thank Gauss for that, don't we? So the same with your infinitesimals. You give it a name, and then you remember that its square is still a small and even a smaller number, and so on. So I was trying to save you from the question, and that's all I wanted to jump in with, if that's all right.
May I?
Sure.
I loved what Adam said about the square root of -1. I can remember vividly being about 12, it being emphasized to me that negative numbers didn't have square roots. And then I got into the sixth form and discovered that negative numbers did have square roots, and this involved this thing called I. And I can remember thinking that that was a bit spooky, but I trusted my maths teacher. I was very well taught, and got thoroughly comfortable with it. And then I learned about alternating current in physics. And where would we be without electric light, ladies and gentlemen?
In the dark.
We would be in the dark, precisely. Ordinary life would come to an end if it weren't for alternating current, and we have 50 cycles per second. And do the math, as the Americans say. You need complex numbers to do the mathematics of alternating current. A very good example drawn from physics and indeed reality. But to me, an even more compelling example is drawn from straight mathematics half a century earlier. Mathematicians stopped worrying about the square root of -1 when Cauchy invented complex analysis, which is so wonderfully powerful. Calculus is fantastically powerful. Calculus is the most powerful single weapon we have. Not all of you will know calculus. Now, nobody can tell me I'm prejudiced against people who don't know calculus. I'm married to one. I am the father of 2. But I know calculus, and my eldest son knows calculus, and it's wonderful. I cannot plug the virtues of calculus enough. But what is a fantastic leap beyond that is complex analysis, which is taught in the second year in a straight mathematics curriculum, and it opens up enormously powerful possibilities. And those of you who've had it will know what I'm saying. Those of you who don't, try it sometime. You will love it, ladies and gentlemen. I really mean it, you will. It was that stopped mathematicians worrying about it. Just do it. Just do it. That light would go out if people were still worrying about the square root of -1. To close on a note of mild controversy, you can do calculus perfectly well without using infinitesimals, but I'm done now.
So one thought might be that the development of calculus is understandable historically as responses to a series of objections. So, you know, you have Berkeley's initial objections to...
he was a bishop. What do bishops know about mathematics?
Well, listen,
I mean,
he
one
did
of these
this
old
for a
religious
reason. He
mathematicians.
didn't knock Newton just to knock Newton. he wanted, as I understand it, Tim...
No, Claire's the expert.
Yeah, well, sorry. Yes, of course. The scientists were trying to knock religion. And he said, but they're cheating. They say we're cheating, but they're cheating too. So he spent a lot of time essentially defender of the faith, you might say. Yeah, Henry VIII again. Sorry.
Cheating, wasn't he?
Well,
He wasn't defending cheating, that's what he was doing.
something like that. I dare not go
He was
beyond...
attacking people who were attacking his thing, which was religion.
Exactly, yeah.
The thought was, if mathematics can't pass a test, then it's unfair to apply that test to everything else. But even with Maclaurin's
He who
response...
from sin is free, let him cast the first stone, as it were.
Well, yeah, but let's face a sort of phenomenon in mathematics that's worth just spending a couple of moments about. We talked about the paradoxes of yore, the flight of the arrow, how can it fly, and so on. This was the mathematics of the Greeks, who knew how to work out areas and volumes, but didn't have the slightest idea of these infinitesimals. And what I wanted to say here was, if somebody as great as Newton was unable to give a kosher account of what was happening, and it took quite a lot of time to clean up, then it's not really surprising that this happens in other areas of mathematics, which initially are generated, and this is the point that was made much earlier in response to your question. Mathematics isn't about numbers only. It's about structure, it's about concepts. And sometimes it takes a very long time to wean these concepts out. To answer the paradoxes of the Greeks would take centuries, but they're answerable now, at least to my way of thinking about it. And then just to give a plug to what Nick was saying about the beauty of calculus, it's simplifying process. Can I make two comments? The first is to give you an example. Do you remember the old story of Gauss the young Gauss at school being told to be busy and add up all the numbers from 1 to 100?
The punishment, wasn't it?
And he did it rather quickly by writing them backwards as well, and then adding all the two rows together and said, I know what the answer is. He had a formula in effect, and it said 1/2 n into n plus 1, right? So it's a half n squared plus another bit, and the formula tells you how to compute. Now, imagine adding up all the real numbers from 0 to x. Now, what do I mean by adding up all the real numbers? Well, he doesn't, but he will say, imagine how you build the holy books. Lots of very, very, very thin, i.e. very small, i.e. infinitesimally thin pages that actually add up to something. So there's an appropriate calculus of how to add these infinitesimals together, and the formula for adding them all up is an idealization of the Gaussian formula, except that it's so much simpler. It simply says 1/2 x squared. None of the extra bits and pieces. It's the simplicity of the calculus that makes it such a wonderful weapon to deal with problems. Can I mention, because this seems to be so far, so remote from the London School of Economics, to say that accounting theorists at LSE, for the most part, and this is an old tradition, don't like to go beyond what you might call modeling with two-period models. Why? Because trying to model with a three-period model, imagine...
Can you just clarify for me what the two-period, three-period...
Yeah, okay, so the year is a four-period model, right? The 4 quarters of the year. And if he had to figure out what happens in the 4th quarter, he'd find it rather difficult without a computer. And so the modeling is done with just 2 quarters, as though the end of the accounting year was the middle of the accounting year. It's so difficult that they just stick to these two-period models to describe when is it optimal to disclose information to the market and so on. But the calculations are so horrible because they're using discrete time, whereas these things can actually be done in continuous time, and the formulas for the same accounting models have an immaculate simplicity to them. I don't want to bore you with this, but that's a fact. And that's how it is. When you can't put calculus into it, you're going to go in through difficult calculations, which are then basically the computer has to do them. Enough of the plug. Sorry.
So I'm just wondering at this point if anyone has questions again. So we've done a lot on infinitesimals there. Okay, this gentleman.
Thanks. This is all really fascinating. So thank you. My question is about someone mentioned the bushels of corn and the kind of as part of the historic utility of mathematics in society and science. I'm kind of wondering, and maybe this is a question for the philosophers, do we have any sort of evidence as to how essential an understanding of numbers are to kind of human consciousness? Are they socially constructed, even if they're socially constructed in almost all societies, or are they something that we kind of know about and experience essentially? And I'm kind of thinking of, I've sort of heard stories of Amazonian tribes that can't count and stuff like that. They're kind of like, oh, there's one and then there's loads, How much evidence is there about that?
They come up a lot and early on. So yes, you do hear the stories of tribes that don't have much of a concept of number, but there's also evidence that babies do something that's a bit like counting. They have expectations. So if you show babies two puppets and then put a screen up and then show one of them going away and put the screen down, they're surprised. They look longer if there's two puppets left as opposed to if there's one puppet left, because they think that 2 minus 1 is 1. One way of thinking about that is that they have numerical expectations. They're kind of responding to the numerosity. So there's some evidence that babies have some kind of numerosity instincts, ability to pick up on numerosities in the world. Animals as well. So birds seem to be able to keep track of numbers of eggs and things like that.
A certain number.
Up to a certain number, yeah. So it seems for humans, I think we can see at a glance up to about 5, that there's 5 things. When it gets a bit further, then we need to, there's something else going on in our brain. So we certainly have, it looks like we have brain machinery that makes it natural for us to respond to numerosities in the world. That doesn't mean that that all humans in all contexts would then develop mathematics, but it's something that looks pretty basic for us, and certainly as soon as we start exchanging goods and that kind of thing, it becomes important for us to keep track of those things. And there's so there's a nice story about how Babylonian maths, if I remember this right, how the Babylonians developed their number system. So when they were exchanging things, they used to try and keep track of who owed who, how many sheep or whatever. So they'd have a little box and they put a bunch of clay balls in the box to correspond to how many it was, and then you could bring it back and say, okay, well, that's open the box and you see, okay, that and that, 3 or whatever. And then they realised that they could just sort of avoid breaking open their boxes by putting their tokens in the box, but then putting marks on the box that correspond to the numbers of tokens that they have in the box. And then they kind of realised that once they'd done that, they didn't need the tokens anymore, right? So and then we get this nice sort of number system that's just sort of strokes on a page, kind of like tallies, I guess. So there's certain human interactions that naturally come up in once we have social interactions going that make it very natural to develop a number system, certainly for finite numbers. What that tells us about what the numbers are is hard to know, to be honest. Certainly counting is important to us, but whether those basic processes of counting should be understood as some basic intuition of the numbers that mathematicians go on to study is a whole other question. I'd argue not, but maybe Tim wants to come in on that.
Well, I was just going to say, in some ways, philosophers are terrible people to ask this question to, because because in a way the question is no, not your answer was wonderful, but in a way it's not your answer as a philosopher so much as your answer as we have to know enough about the experimental psychology and anthropology here. Fortunately, you do, and I'm going to throw in with an extra little bit as well. So, Mary mentioned the sort of the tracking business about our ability to keep track of small collections, but it does peter out. So you can't tell at a glance whether the 19 things that were following you have been replaced with 18 or 20 if you look back. And ducks have the same problem. They're fine if there's 3 ducklings follow them, and then if one of the ducklings vanishes, they get concerned and go and look for it.
I have 4 children. I stopped at 4. At some point it gets a bit tricky.
Or is it impossible to count them? No. But yeah, so it seems like there's a sort of 2-stage thing going on. There's the tell at a glance thing that we can do with really keeping track of specific objects, and then there's a sort of hazy more than or less than before. So if you're being chased by 40 ducklings and it dropped down to only 20, you'd probably realise, but you might not notice things at the edges.
I'm okay now. There's just 20 of them.
Right. How many ducklings would be? No, that's a silly question. The thing I was going to mention is it's then a question about how far you go with that in different societies and different cultures to developing serious mathematics. And I take it one of the things we probably all agree on is that for it to become serious mathematics, it's accepting the infinity of the numbers. And that's not, it seems, straightforwardly built into just the cognition of, well, I can keep track of 5 objects and tell at a glance that there are 5 of them. Thinking that there are infinitely many is this big extra step. But there are good questions as to how exactly that happens, and there are some pretty good accounts of why it would be quite common. But I'm going to leave that tantalisingly there as something for someone who's...
I'm just going to invite the mathematicians to make a quick response, because I want to move on to our next topic, which is very relevant to this. So,
I'll just say pixels on your screen. You don't see enough of them unless you work hard to look at them, and they give you the impression of continuity. And this is exactly what we're talking about when we're saying that Newton took what he must have presumably thought of as a much more discrete world. We don't know, but I'm guessing he would have done, being the wise man he was, and essentially was saying to himself, but I can take this discrete world and model it with these infinitesimals so that you must imagine that Newton would have had a view on the paradox of the arrow. I've never known, but maybe colleagues here do.
He abstains a bit on the metaphysics stuff, doesn't he, Newton, I think?
That and the mere fact that you go into a cinema and can watch a film, which is
16
again
frames a second.
exactly, which is again based on enough discreteness, just like with the pixels, to create the perception of continuity. Which perception of continuity we, the mathematicians, have abstracted out of the real world in order to do work with it, and Newton has shown us how wonderful it is in terms of telling us, about the cosmos.
Yes, thank you, Adam. To answer your very nice question, sir, the other night on television, I think it was David Attenborough was talking about bamboo, which flowers only rarely. And he said something about kinds of bamboo that flower every 105 years or so, but colonies of bamboo in different continents flower at the same time. How do they know? I don't know how they know, but 105 or 110, whatever the number is, it's specific to a certain kind of bamboo. And how the hell does it work? I don't know. I'd love to know. The other thing I'd like to pick up on is what Adam said, discrete versus continuous. To do calculus, you have to think continuous. Indeed, to ride a bike or drive a car or run, you have to think continuous. But when you're handling data, you either have to do it by hand, but you're discretizing. When you write numbers down, you have to truncate the damn things, because a typical number goes on forever and life doesn't. So you have to truncate, and computers work discretely anyway. And we go back and forth, every day between discrete and continuous, and we take it for granted. So there's no war between the two. It's just how we are.
I'd like to take another question at this point from the audience. This one here.
I was thinking about that question about whether children know about numbers and whether animals might know about numbers. And I'm just thinking about what an animal does when it's just deciding a foraging strategy, because it's got target berries or nuts or other animals that are moving around, and they have a value, a nutritional value, and that each event of picking one up is a cost to that animal in terms of its own risk to another animal spotting it or another animal getting in there before you can get it. There are lots of simultaneous variables there, but animals are actually solving that problem because they're doing the most economical foraging strategy that they can, and that's been shown by many animal behavioural studies. So it seems to me that within our brains, that like all this maths is to do with structures in our brains, and those structures can be produced in two different ways. In the course of evolution, or in the course of experience. There are two different logical mechanisms going on, and actually they can come to theoretically could produce the same brain structures operating in the same way. It just depends which is the most economical for an organism to have followed. So it seems to me that the main difference between us and animals is actually we give names to the numbers. And a rook doesn't have to do that. And a bee doesn't have to do that either. But they have maths going on in their structures.
Yeah, can I come in on that? So foraging is a nice example. You mentioned bees, and there's a very nice example of the structure, the honeycomb structure of hexagons, where it looks like bees have come to a mathematical result that actually is called after them, the honeycomb conjecture. It's now proved that says that the hexagon is the most efficient shape if you want to tile a two-dimensional space, and I guess if you're going to do a three-dimensional space but do the same tiling across, then that gives you the shape of a honeycomb. So there certainly are cases where animals seem to have worked out these nice mathematical results for themselves in some way. Another one I'd like to mention is cicadas, which has to come up. Tim's laughing because it has to come up in any philosophy of maths talk nowadays. So I don't know if people have heard of these insects. So in North America, there's these insects that the periodical cicadas that have a very long period. So what happens is the eggs hatch and the grubs live underground for many years, foraging on roots, and then they emerge as adults, as these sort of flying creatures. These insects that fly about and mate and lay their eggs, and the eggs hatch again, and so on and so on. What's interesting about these creatures is they have a very long life cycle. So in northern states in the US, the periodical cicadas have 17-year life cycles. So you'll get them appearing in maybe 2000 and then in 2017, and people wait thinking, okay, the cicadas are coming, and they all appear en masse after 17 years. If you're in the warmer southern states, they appear every 13 years. And again, it's kind of like clockwork. People can predict they're going to come, and indeed they do. So they all manage to emerge at the same time, and that raises an interesting question. Well, why those length periods? Why 13 and 17? Well, one thing interesting about 13 and 17 is that they're both prime numbers, and this led biologists to conjecture the following about the evolutionary history of these creatures, which is, well, if we think back to their evolutionary history, imagine that there's a whole bunch of periodical creatures around, and imagine that it's advantageous to avoid overlap. So maybe you've got predators that are periodical, or perhaps more likely, maybe there's other insects that that are similar enough to you that are periodic that you could mate with, but your offspring would not be viable, and so on. So it becomes advantageous for these creatures to avoid overlaps with other creatures. And once we hypothesize that, then it becomes fairly easy to see why choosing a prime length period is a good one, because prime numbers are going to minimize overlaps. So if they chose 16 years rather than 17 years, then they'd overlap with all the 2-year and the 4-year and the 8-year creatures. But if they choose 17, they're only going to overlap with creatures with multiples of that. Yeah.
Just maybe wait for the microphone so we have it for the podcast.
I'm going to suggest that when the House of Lords is reformed into an elected body, that they should have 7-year terms. For this very reason, the Commons will be up to 5 years, and if a Prime Minister wishes to call a Commons election to coincide with the 7-year Lords election, they're going to lose time in power.
Right.
Tim, did you want to jump in?
Yeah, just very quickly, going back to the original question. You're right, I think, that there's an awful lot of mathematical processing that's going on. But you said that the main difference between us and the rooks is that we name the numbers and that they don't have to. I think there's maybe just a little more I'd want to add than that. I mean, if you think about classic example of David Beckham taking a free kick, you can explain this in terms of an extraordinarily complicated calculation in mechanics, using an awful lot of calculus to work out exactly what swerve he wants. Or you can just think he's practiced an awful lot of times and he's incredibly skilled. And there's very little by way of conscious mathematical calculation that's going on there, but presumably this can be well modelled by a bunch of mathematics that we could do if we were, as mathematicians, modelling him. And I sort of want to say a bit the same about the rooks, that whilst we can model it using lots of mathematics, that doesn't necessarily prove that they have much by way of maths going on. It just proves that maths is an extraordinarily powerful tool in general for modelling stuff. So just a slight dampener on the question of exactly how much mathematics rooks can do, but they're pretty impressive in lots of ways, so it wouldn't surprise me.
I think snooker too, right? The thought is, one way of explaining what's going on in a snooker interaction is purely geometric with classical mechanics involved.
I thought you had snookers playing rooks.
Maybe I'm wrong.
I mean, I wouldn't be surprised. They're very sophisticated.
They're a sophisticated breed.
Over there.
Okay, so we'll have to just wait for the microphone.
That mathematics is really just a set of programs of some sort, be they on paper or not. I mean, is there not, aren't you sort of avoiding that there are sort of quite mysterious and quite baffling ontological questions that treating maths as merely as a program, that the natural numbers are just, one number plus the next one, that's a program. The fact that it can go on forever is purely coincidental, if you like. It doesn't, if you're talking about programs, it doesn't answer about the ontology or existence of infinities and greater orders of infinities, which are, again, could be part of bigger, more complex programs.
Okay, thank you. We're going to take this question with one up here as well.
Hello, thank you. I don't share your faith in mathematics as the other of religion. As someone like, I think Richard Dawkins comes pretty close to making a religion out of rationality, which is obviously something that is inscribed within mathematics. I happen to do research for peculiar reasons into this question of rationality and its relation to a certain kind of Eurocentric worldview. And I stumbled across an awful lot of white supremacist websites dedicated to proving that black people lack the intellectual rigor to do mathematics. And I've heard similar things said about women. So it can actually constitute the basis of a witch hunt, contrary to what you said. And I'd just like to hear your comments on that. Another aspect of it is the relationship between mathematical languages, if we could call them that, and so-called natural languages or national languages, where the difference, the unheard difference between the word whole, meaning a totality, and whole, meaning nothingness, caused a hell of a lot of confusion for some of the people that I taught mathematics who had English as a second language.
Okay, thanks. So 2 questions there, well, 2 main questions. One sort of on the ontological question, and another on maybe the way in which mathematics is weaponized in certain contexts and how it's been co-opted by a certain rationalistic movement as, along with logic, it must be said, as sort of the unique preserve of certain groups or something.
Yeah, I'll just chime in only on the last of those and about the... because it sort of ties in with what I said before. Mathematics is extraordinarily powerful, but as Spider-Man taught us, with great power comes great responsibility. So it's unsurprising that it gets weaponized in these various ways as well. And I just want to offer 2 different historical examples, because I don't think there's anything you can do in these cases except offer historical examples and then look at the dangers. So the first historical example is it's a fairly notorious attempt by the Indiana state legislature to establish by legislative fiat the value of pi as 3.2, which was unwise. And there has to... there's an awful lot in the background as to why one might even begin to start doing such a thing. But it's complicatedly tied up with certain views about religion at the time. And that just looks completely bonkers to us, but it happened. It didn't actually... the bill didn't pass, fortunately. The other, just coming totally from the opposite side, is a dream that a bunch of philosophers / physicists / mathematicians had in Vienna in the late 1920s, early 1930s. So they wanted to create a universal language of science, which would have logic and mathematics right at its foundation. And they had many reasons for wanting to do this, but one of them was an opposition to totalitarianism. They thought if there was a single global unified language for science, it would be that much harder for people to hoodwink the masses by flowery rhetoric or something like that. And it's a fascinating vision. It involves them being involved in things like the movement to get Esperanto up and running. One of them comes up with a system of signs which is meant to have a sort of certain clarity to them. They're doing all sorts of things simultaneously. And of course, what happens a few years later is that the Nazis come to power. These philosophers and physicists and mathematicians are some of the few people who stick around in the German intellectual milieu and resist Nazism. They go to the German Congress of Philosophy in 1934, and they say the philosophy of National Socialism rests on a mistake. It's a philosophical confusion, and they're trying to hoodwink you and smuggle in, at the same time as confusing you, all these horrible racist bits of ideology. So they reckon that mathematics is going to be this tool of clarity, and it's going to get everything nice, and there won't be any way of deceiving people if you just state things clearly enough. And I guess I'm just pessimistic and think, you can lie with statistics, and you can lie with any bit of powerful language that you have, and mathematics is just a very, very powerful bit of language. So it doesn't surprise me that people try and use it for bad, and equally that people try and use it for good.
I think we might have a contrasting set of opinions on the table about the ontology matter. So
sorry, I didn't
maybe
speak
do you
about
want to start to answer
there was
question?
There was this question about mathematics being algorithmic, and I wanted to just drop a line into that. I think, well, that's what a lot of people want mathematics to be, especially undergraduate students. They don't want to think. Now, some of them. Or maybe we don't persuade them enough. Anyway, I just wanted to come back to your business about the insects, which is really about knowing how to avoid certain periodicities. And this leads you actually to questions about how well, given that you're looking for periodicities, how well fractions can approximate non-fractions. And the amazing thing is, number one, the proof about this, which goes back to a name, Tue, I think is the correct pronunciation, and it is heralded as one of the most significant theorems in number theory, which you would have thought was, pretty, concrete sort of stuff, that has a non-constructive proof. Paul Cohen, who dealt with the continuum hypothesis, had always been inspired by this since his very early youth. This is only to indicate that although we tend to concentrate in talks like this on the more simple algorithmic features of mathematics, because they're more easily communicated to an audience, on the other hand, we are always at pains to try and understand something, and the creative spirit of mathematics, the construction of new concepts or structures with which to understand reality, is actually what mathematics is more about than just, plain accounting with numbers.
I think these two thoughts are related. So, Mary, the cicadas and the honeycomb conjecture, they've been used to by a certain sort of group of philosophers to suggest consequences for this sort of realism, anti-realism question that's raised over here.
Yes,
we'll have time for the full discussion.
Sure, but
a sense of
yeah,
that.
So I have to confess that I'm one who is tempted by the picture that you were laying out of mathematics is just being about working out the consequences of certain assumptions, and what was mentioned is maybe the algorithmic view. The thought being that when you do maths, you just write down a bunch of axioms and then you work out what follows from them, and who cares? As Russell said, mathematics is a subject where we never know what we're talking about, nor whether what we say is true. Doesn't matter whether the axioms are true, we're just working out what follows from them. And one of the main challenges to that view, which I have to say I would like to defend, comes from the use of mathematics in science, because it looks like, unlike internally in mathematics, where it's we can just think of our mathematics as involving working out what follows from axioms. When we use mathematics in science, it looks like we sometimes appeal to mathematical objects in explaining things. So when I explain the cicada behavior by saying, well, it's because why are their periods as they are? It's because 13 and 17 are prime numbers. How on earth can I give that explanation if I don't believe that there are numbers? It looks like that's an explanation that's not open to me if I don't believe in numbers. So that kind of example has been presented and pushed, and the honeycomb case and foraging examples and so on have been presented in philosophy of maths as a strong argument for taking a more substantial view of the ontology of mathematics, because it looks like when we use mathematics in science, we're not just working out what follows from what, we're actually appealing to mathematical objects and their properties in explaining phenomena. And to the extent that mathematical objects and their properties are appealed to in our explanations, they are a bit like the electron in the cloud chamber, which explains why we see the track in the cloud chamber. Right? So I explain the track by saying there's an electron there. I explain the cicada behavior by saying it's the primeness of 13 and 17. That's how the argument's meant to go. I'm not convinced by it, because I think actually when we try and uncover how mathematics is playing an explanatory role in these cases, we get something quite different. But that's meant to be one of the strongest arguments in philosophy of maths for saying we have to take the ontology seriously and not think of this as just a kind of if there were these things, there would be these.
Yeah, just very quickly. I mean, I'm almost deliberately dancing around the issue of whether or not the mathematical objects exist. Because, to quote a line from Kreisel, the question is not about the mathematical objects, it's the objectivity of mathematical truth. So the algorithmic view that you mentioned has certain demonstrable limitations. Algorithms can only take you so far. If you're familiar with it, the halting problem is basically the limit of what you can do with algorithms. So there's a serious question about how many mathematical truths you could get out just via an algorithmic approach. But when it comes to whether or not the objects themselves exist and what we mean by saying that they exist, I'm sort of willing to shrug and say I don't really care, so long as I'm allowed to say these mathematical claims for free and say, yep, they're okay, they're true. Don't care about whether there are any objects floating around behind them or not. Why would I need to worry?
I just wonder if anyone on this side of the table does care about that particular issue.
I'd like to close by saying two things. We haven't got much time. One, the great Hungarian physicist Eugene Wigner wrote a paper once called The Unreasonable Effectiveness of Mathematics. Some of you will have read it. Those of you who haven't, I'll say it again, slowly enough, write it down, Google it, read it, The Unreasonable Effectiveness of Mathematics. It's wonderful stuff. The other, one of my colleagues on the panel, talked about bees and honeycombs. Have any of you seen the Giant's Causeway in Northern Ireland? I wish I had. Before I die, I want to go and see the Giant's Causeway. Cooling basalt. Basalt doesn't think, but basalt knows how to cool, and it's the same piece of mathematics. Thank you.
Okay, well, I think we're just at time there, so it just remains to thank our speakers, and maybe particularly thank Nick, whose birthday it is today.
He's a jolly good fellow.